In this video, we are going to cover the theoretical part of a variational autoencoder. So the motto of variational autoencoder is sampling from a normal distribution. So we are going to deal with the normal distribution in this architecture. But first, let's see the reason why do we need variational autoencoder. So one of the big limitation of standard autoencoder is that it can't be used for generating new images. And the reason is that the latent space is unbounded, and because this latent space is unbounded, it is going to be huge, very huge, and which makes the sampling process really difficult and challenging. For example, imagine if you have a latent space of like 64 dimension and it is unbounded. So in each dimension, the values can theoretically be ranged from negative infinity to positive infinity. Then how you are going to sample some random values or random sample from that big huge space in order to feed to the decoder for generating new images. So it's basically a challenging task. So we need our latent space to belong to some distribution so that sampling becomes an easy process. And one of the most commonly used distribution in all machine learning and deep learning is the normal or Gaussian distribution. So that's why variational autoencoder uses that distribution for sampling. So let's see the features of the variational autoencoder. They were invented in 2014. We are going to sample from a Gaussian distribution, and the latent variables will be used as mean and standard deviation. This is a general diagram of how variational autoencoder works. First of all, we have the encoder, and this encoder is going to output two latent variables. One is going to be mean and other is going to be standard deviation, and these could be scalar, but in most cases, like in 99% cases, these are also high dimensional vectors. In our case, these are going to be 64 dimension each. So mean is going to be 64 dimension and standard deviation is going to be 64 dimension. And with the help of this mean, standard deviation and normal distribution, we are going to sample, and then we will feed that sample to the decoder for generation. So this is the general diagram of how variational autoencoder works. The architecture is going to look very similar to the standard autoencoder, but we are going to make some changes in this sampling part. Let's start the discussion with this line: sampling is not differentiable. In order to understand this concept, let's see how TensorFlow calculate gradient. So basically TensorFlow create a computational graph, and based on that computational graph it calculates all the gradients, and which we use in the back propagation algorithm. But if we use the mean and sigma, which are coming out from this encoder directly into this sampling distribution, then the distribution itself is not differentiable, and our graph, our computational graph, will break right here, and our back propagation algorithm will not update the weights of the encoder. So in order to solve this problem that sampling is not differentiable, we use a trick called reparameterization. So what reparameterization does: first of all, we are going to sample from a normal distribution. As you can see here, n represent our normal distribution, 0 is going to be mean, 1 is going to be the standard deviation. Then we are going to multiply that sample with the sigma and then add our mean. So this mean and this sigma are basically the latent variables which we will get from this encoder. And with the help of this equation, now our model will be differentiable and the back propagation algorithm will work fine, because now it's just an affine transformation, and affine transformations are differentiable. So this is the reparameterization trick. And now let's talk about the loss function. So in case of variational autoencoder, we have two objectives. First, we need to create a less noisy images, and then we also need to make sure that our mean and standard deviation should belong to 0 and 1. The mean should be very close to 0 and the standard deviation or variance should be close to 1. In order to achieve the first objective, we are going to use a reconstruction loss. So it could be like mean absolute error or mean square error or binary cross entropy. So in our case, we are going to use binary cross entropy. And in order to achieve the second objective, that is to make sure that our distribution is close to normal distribution, we are going to use Kullback-Leibler Divergence loss function, which basically measures the distance between two probability distribution. And we will make sure that the distance between our distribution and the normal distribution is less, and which makes the sampling process easy. So this is going to be the reconstruction loss function. It's a very standard binary cross entropy, while this is going to be the Kullback-Leibler divergence loss function, which is negative 0.5 into tf dot reduce mean. So if you go to the internet, you will find the mathematical formula of this divergence loss function. This code is basically the TensorFlow version of that formula. Exponent will convert this log variance into variance. So in the upcoming slides, we are going to discuss the reason why we need to use here log variance instead of standard variance. But first, let's see the coding of how the encoder is going to look like. So the latent dimensions are going to be 2. Sorry, in the first slide I told you it should be 64, so I was thinking about the celebrity dataset. In that case, I have used 64 dimensions, but in case of MNIST, 2 latent dimension for mean and log variance will be fine. So we are going to have a convolutional layer, then another convolutional layer. So in this case, I have defined stride to 2. This means we don't need to use max pooling. And then I'm flattening my data, and from that flattened array, I'm going to calculate the mean and then the log variance, not a simple variance. And we are not using any kind of activation right here. Now let's talk about the decoder. It's very standard decoder code. First of all, the dense layer will have 7 into 7 into 64 units. Then we are reshaping it. Then we are using here convolutional transpose. So again, you can experiment here with upsampling as well. It's totally up to you. So the output from this transpose convolutional 2D will be 14 by 14 by 32, and the output from the second transpose convolutional layer will be 28 by 28 by 1. And now let's talk about the sampling code. So these inputs will be provided by our encoder model. Encoder is going to return the mean and log variance, which we are going to accept right here. And then this is our random normal distribution or Gaussian distribution. The shape of all of these three variables, the mean, the log variance, and epsilon, should be same. And then we are just multiplying the epsilon with the variance and then adding the mean. So this tf dot exponent will convert our log variance into variance. Let's talk about the reason why we are using the log variance instead of variance. So the main reason is this numerical stability. And why numerical stability? Because in the dense layer we have put the activation to none. This means the variance will have no constraint on it, and it can be negative and it can be very large value, which makes the learning hard. So that's why instead of using it as a variance, we will treat it as a log variance, and we'll use this tf dot exponent in order to convert that log variance into variance. So I hope you have understood the theoretical part. So in variational autoencoder, there is one important thing, and that is sampling. We are sampling from a normal distribution. Then we are using two different loss function, the reconstruction loss function to improve the image quality, and then the divergence loss function in order to make sampling process after training easy, so that we could generate some new data using the variational autoencoder. So I hope you have understood, and in the next video we are going to implement its code, and I'll see you there. Bye bye.